One. All right, hi. Welcome back once again to Math 234. I am your host, Steve Dragoo, back again after a brief absence. So again, I wasn't here Friday, but you could have had a substitute that was here covering parametric surfaces. I also recorded a video of my own if you wanted to keep going through the same notes we've been doing. But I had to record it on my own in an office somewhere. So I think it came off a little unhinged, but it still got all the material in it. So if you needed to go back and look through these specific notes for the parameterizing surfaces lesson, that's on D2L. You can find it where all the other videos are. I just pretended like it was September 26th. But today we've got the chain rule. And probably that sounds familiar because you've already got a version of the chain rule. In particular, you've got just the standard Calc 1 chain rule derivative method. It's one of the first things we learn, sort of right after the product rule and the quotient rule. We then go into the chain rule. And in Calc 3, it's going to be pretty similar. Just anytime we have one function inside of another function, we're going to have to multiply by some extra derivatives. And that's why we covered parameterizing surfaces when we did. It's because that's a really nice lead in to the chain rule. Because now we might have a function, maybe z is a function of x and y, but then x and y can both be parameterized, so maybe they're functions of s and t. Meaning if I try to take a derivative of z, I'd have to do my x and my y partials because that's the way that we do those sorts of things. But also, since x and y are parametric, they'll depend on s and t. I'll need to take derivatives of those two variables as well. I'm going to take a derivative of x and take a derivative of y with respect to the function that's being plugged into them. So the regular old chain rule, y prime is equal to, well, let me back that up. Dy dt would be dy over dx times dx dt, but really, maybe another way we would have written that out from Calc 1 would be to say that this is like f of g of x. And I want to take the derivative of that whole thing. That's just f prime of g of x times g prime of x. And we want to roughly rewrite the same thing. But to maybe make it look a little bit more like the variables we'll be using, maybe I'd call that y of x of t. Make sure I get enough parentheses on there and take its derivative to get y prime of x of t times x prime of t. Right, that was our chain rule from Calc 1, and we'll basically be doing that again, except multiple times. So if we maybe skip up ahead to a few of the things we might look at, maybe we'll have some function that has, call it w. Here's one of the imagine ifs we'll look at. Our function might be a function of three different variables. Or we might have our normal z equals f of x and y, but then x and y are functions of variables themselves, being s and t, part that I was just talking about a second ago. So I think the best way to get through this unit is to just do a few examples. So let's go do that. So our full formal definition of the multivariable chain rule probably is something like this. If I've got my function that's w, and it's a function of three variables, x and y and z, but each of those variables, x, y, and z, can be parameterized using t, then our differential, or our full derivative of w with respect to t, is going to be made up of an x, a y, and a z partial. Then each of those partials need to be multiplied by the chain rule part. Right? Chain rule part is that dx dt or that dy dt or that dz dt, because I've got some other function being plugged into x, y, and z. That thing is parametric. So I'm taking its derivative with respect to t. So we'll do what we can to keep track of all of our variables because we will be looking at just a ton of them through this unit. So if at any point something looks a little confusing, just stop me and ask a question. To fill out another table, z, or whatever thing we're defining as the function is equal to blah, z is going to be our dependent variable. In the case where we're looking at our parametric surface, or parametric equations with s and t, that makes s and t our two parameters. Those are going to be our independent variables. And here we're calling x and y the intermediate variables, but maybe it'd be better to think of x and y more as functions in their own right that are being plugged into f. So if I'm trying to make an analogy back to the chain rule that was f of g of x, x and y are going to take the place of g, the function that gets plugged into f. And again, it'll have its own two parameters, which are probably going to be s and t. Oh, right. Let's draw some tree diagrams. So that was the last thing I wanted to do before the first real example. So tree diagrams can be helpful with trying to keep track of what sort of derivative parts we will need. So looking at the two spots above, I had my function w that was made up of an x, a y, and a z function. Right? W is f of x and y and z. So I'll put those three variables along the first branch of the tree. And then each of my three x, y, and z intermediate variables or functions are all functions of t. So if I were to try to find a path through to the end for taking the derivative of w with respect to t, I would need first three partial derivatives, one for x, one for y, one for z. And then each of those need a derivative with respect to t. At that second example, what did we call you again? You were just z, right? Yeah. So in that second example, where I've got a z being a function of both x and y, x and y. So again, that'll be my intermediate step. Branching out from those two variables, I have s and t. Because again, I'll think of x and y as if they were functions being plugged into z. I'll keep another s and another t here. And so my actual independent variables are all of the letters down at the bottom of the tree, the time I made at the end of my tree diagram. So I'm going to be looking at taking derivatives of my original function with respect to one of those variables, one of my parameters. Let's just say I'm going to look for dz dt. So example, find dz over dt, or the derivative of z with respect to t. What I would do is trace my tree diagram from the top to the variable that I am looking to take a derivative of. So I have to come out of z and take an x partial, and then from there, get its derivative with respect to t. I also need a y partial, and then get its derivative with respect to t. So think of it sort of like a Plinko machine. I need to drop a bunch of, I don't know, are they Plinko balls? Drop those in at the top and watch them fall all the way down so that they land in every pocket where I've got a t. So every intermediate variable, every intermediate function that has t as a parameter, I need to follow my tree diagram down to that letter. Now with that built up, let's actually go do an example. And the first one, conveniently, will have an s and a t in here as our two parameters. And our goal is going to be to find a derivative of my function, which is z, with respect to those two parameters. One with respect to s, one with respect to t. So some of the things that I'm going to need. I'll need lots of derivatives because the chain rule is just going to be built up of a ton of them. So I will start by taking the derivative of z with respect to its two intermediate variables, right? I'm just going to find z prime or z prime. I'm going to find z partial theta and z partial phi. Those are the two steps I need. So z partial theta looks to me like it'll be cosine theta times cosine phi. And again, I'm going to put those in gray because I'm going to keep in mind that those pieces are my intermediate variables. They won't ultimately end up in my answer. They're just a tool for me to get there. So the other bit I need, z partial phi. If I take that derivative, I think I get sine theta times negative sine phi. Let's call it negative sine theta sine phi. Those were the two intermediate variables of the two bits that I am plugging into z. Those are the two functions that are going directly into my z function. I know I'll need both of those partial derivatives to talk about any sort of a chain rule. So get those done. Then I'm going to come over and find partial derivatives of theta and phi with respect to s, if I'm going to look for dz ds first, which I think is going to be t squared on the one side. If I do the derivative of phi, and if I do, or derivative of theta, I get t squared. And if I do the derivative of phi, I think I get 2s times t. Just the derivative of s squared is 2s. And then to just complete the chain of all the derivatives I'm going to need, because I think at that point it'll be exhaustive. I'll take the derivative of both theta and phi with respect to t, both of those partial derivatives, and I get 2st for the theta partial, and I get s squared for the phi partial. Cool. So hey, look at that. Whole bunch of derivatives. Now let's go combine them in the way that we want. So starting with a tree diagram, maybe put a, nope. Let's put a z over here. Z I know is a function of both theta and phi. Theta and phi. And I've probably put you just a little bit too close to the edge there, so I'll slide it over. And then each of those two intermediate variables, phi and theta, I'm going to think of them as functions of s and t. And since I'm going to be looking for a couple of derivatives here, I'm going to create a copy of my tree diagram and just move it out of the way for right now. I'll come back to it in a second. So, thinking about this thing first, I would like to get a derivative of z with respect to s. So, the first thing I want, and I'll write this out in our shorthand notation. I want z partial s, which that's going to look like. First, a derivative of z with respect to theta. Right? Because anytime I want to take a derivative of z, at least without substituting a whole bunch of stuff in over there, I will need to take z's partial derivatives with respect to theta and phi. I know if I want any derivative of z, I need to start there. I need derivatives of sine theta, and I need derivatives of cosine phi. But they're partial derivatives, so I'll keep them separated. So where I took the theta derivative, I'm going to need to multiply that by the derivative of theta with respect to s. Because again, theta is the function being plugged into z. Anytime I've got a chain rule or I've got a function chained inside another, you need to multiply by the derivative of the inside. In this case, theta s. And I want to add to that the other half, which is the derivative of z with respect to phi. And then I'll multiply that guy by the derivative of phi with respect to s again. Right. So those are all of my chain rule derivative elements. And now I'm going to just bring everything in. So step 1, I've got cosine theta, cosine phi. And then I need to multiply that by the derivative of theta with respect to s, which is t squared. T squared. Plus, adding in another element here, this is negative. Negative sine theta, sine phi, times s squared. Nope. Try again. That's 2st. That didn't take long. There we go. So as I'm looking through my s partial of z, I'm not using any of the t partials, right? So all of the color involved in this whole mess all had to do with the blue one. If I'm tracking my tree diagram over on the left, again, think about my Plinko machine. I am tracing all of the branches until I can get down to s, parameter that I care about in this case. And while it looks like we're done with the problem, we actually have one last step to go through. Because I have too many variables right now. Right, in particular, I've got a theta and a phi hanging out inside of my sine and cosine functions, but the variables that I want to have are all s and t. So my very last step after I've sort of structured my derivatives together is to just substitute all of my intermediate variables out. I'll know I have a complete answer when I've got everything in terms of s and t and no longer in terms of theta and phi. So this should look like cosine of, I think this is st squared times the cosine of t squared s squared t. There we go. S squared t, right? If I just pull back up for a moment, theta was st squared, phi was s squared t. Of course, we picked things that looked very, very similar to each other to be as confusing as possible. Sorry about that. But we got those two things plugged in for theta and for phi. So let's bring in my t squared part right there. Well, so I just made those substitutions to get theta and phi out. And then repeat that process for the right side. This will be sine of st squared times the sine of s squared t. All of that times 2st. 2st. For the chain rule part. And then I'll zoom back out to put that whole bit on screen. So all of that just to get my first chain rule, the first part of the chain. That's DSDT. Nope, DZDS. That's DZDS, right? Derivative of z with respect to s. All right, all of the stuff in blue. Tried to keep track of my variables with a little bit of color. So the second half of the question was asking us to find dz dt. So basically do the whole thing over, but this time get a derivative with respect to the other parameter, the green parameter. And if I follow my tree diagram, or go play my Plinko balls, they go from theta down to t, and then from phi down to t. So following the diagram, I want partial derivatives of z with respect to theta and with respect to phi. And then each of those, following the next branch of the path, each of those get derivatives with respect to t multiplied in. And since I've already done a whole lot of work to get my s partial, and my z partial or my t partial follows a lot of the same branches, I'm going to start by just copying and pasting the work I've already done. And then I want to talk about how this new derivative is going to be different. So line by line, let's go through it. And I've conveniently left everything color-coded so that all the bits in blue, all the parts that I need to replace. Because I don't want s derivatives anymore, I want t derivatives. But the bones of the problem are all still the same. But now instead of a blue derivative here, I'm going to want a green derivative. Same thing over there. And then also I think that it's going to be a little bit bigger, so I'm going to slide you that way. And then I'll do the same thing in the final line, but let me do this middle one first. So my theta partial derivative and my phi partial derivative did not change because when I was looking at my intermediate variables, I was only considering my derivatives with respect to theta and phi. We had not even considered our parameters s and t yet. So those bits remain the same. I just need to swap out the s partials with the t partials, which were 2st for theta, 2st for theta, and s squared for phi. So for the final trick here, just keep that change moving down below. I just wanted to replace all of my blue with green. So this was 2st on the theta part and s squared on the t part. And I'll zoom that back out to get the whole problem on screen again. So after we did all of that, I'll take a moment to just point out. And here, I'll just keep one of them on screen for the moment. So I can come back up and look at the top parts. If I had simply substituted st squared in for theta and s squared t in for phi, I could have skipped over the chain, well, sort of skipped over the chain rule part, and then just done an S partial and a T partial directly at the beginning. I just might end up with a more complicated derivative that I've got to write all the way out. In particular, if my intermediate variables start getting more and more complex functions, or more and more complicated functions that I'm trying to plug in, the chain rule can be helpful to just kind of keep straight what all of the derivatives are. In this particular case, s t squared and s squared t, relatively simple intermediate functions that get plugged in. But if I had something more complicated, it might be easier to just sort of keep track of taking derivatives of sine and cosine, and just kind of set that bit aside, and then focus on the next derivative in the chain. Sort of the same reason we used the chain rule originally, was a way of just simplifying the way that we think about derivatives. We can take some of that cognitive load off. It's easier to understand what we're doing. Or so I'm going to try to argue. And let's take a look at example 5.9. Suppose f is differentiable and we know all this stuff about it. Find the derivative of z with respect to t when t is equal to 3. So now I don't have functions per se to plug in for all of these things, all of my various bits, but I do have numbers that I can plug in each spot as I work my way down the lines. So if I were to just try and structure my thing all the way out, I want z partial t at 3, which is going to look like, I feel like the light keeps changing over here. It's going to look like something crafty. This is going to be f partial x, since z is going to be f. But this is going to be f partial x at x of 3, y of 3. Multiply that by, this is the t partial, and well, we're in the middle of the x partial right here. So since I just took a derivative of f with respect to x, x is my intermediate function in this case, I want x prime right in here, because that's the derivative I just did. X prime of 3. And I want to add to that the y partial, x of 3, and at y of 3, and multiply that by y prime at 3. So a lot going on in here, but maybe let me just start pulling some things out, putting them in gray so that I can just focus on the bones for a second. I missed a spot. Yeah, okay. So my structure is still my x partial of f times the x derivative plus my y partial of f times the y derivative. Just to kind of keep some of the chain rule bits flowing there. Oh, well, I conveniently put it like basically in the right spot. So you might have noticed I've got this f partial x of 2, 7 and the y f partial y at 2, 7 when my parameter was 3 the whole time. All right, so why all of a sudden are we getting two new numbers being plugged into f and y? But that would be because of, I come back out and highlight something. Those two bits right there. X of 3 is 2 and y of 3 is 7, which means plugging into the function, that function f, I'm really plugging in my x and my y numbers for those two. So this should be 2, 7, and 2 and 7. Just replace those two bits there. So when I actually do go to replace the numbers, it should be f partial x of 2, 7 and f partial y of 2, 7, and not 3 because it's f partial x of 3 and n of y of 3. And well, again, some of these function chains can get a little long and tedious. So let me quit talking about that and just go plug some things in because I know my x partial is 6 and my x derivative is 5. Plus, same thing but for y. The y partial is -8. The y derivative at 3 is -4. And now all of a sudden I just have a bunch of numbers to multiply and add together. So in other words, the hardest part of the whole lesson, just multiply some numbers together. I think that's 30 plus 32. 6 times 5 is 30. 4 times 8 is 32. Add those things together and I get 62. Yeah, cool. I see some people nodding. Thank you. I appreciate that. Cool. So 62. But enough about that. Let's go remind ourselves what implicit derivatives look like. Because that'll play a hand in making some of these partial derivatives a little bit nicer. So say I wanted to find dy dx, or here I'm just going to call it. That light is changing up here. It's just the light directly over top of my desk is flickering. It got worse right now, I think. Anyway, we're looking for dy dx. I think I was in the middle of saying I'm just going to call that y prime for simplicity's sake. So when we did implicit derivatives back in Calc 1, we are going to assume the derivative of x with respect to x is 1. That's the derivative of anything with respect to itself. If it's a variable, ought to be 1. But when I go to take the derivative of y, I'm going to claim that y depends on x, which is why it's an implicit derivative, because there's an implicit y depends on x. So whenever I take the derivative of y, I have to use the chain rule to bring in y prime. So that'll look something like the following. 3x squared plus 3y squared times y prime. Right, so the chain rule says if I take the derivative of y cubed, I also need to multiply by y prime. And that's equal to 6y plus 6x times y prime. Again, anytime I take the derivative of y, I need a y prime to show up. So y prime is the thing that I am looking for. And so in order to solve for it, I'm going to gather up all of my y prime terms on one side and then factor it out. And then divide by everything that isn't y prime. Y prime minus 6x y prime is equal to 6y minus 3x squared. Again, the parts I am focusing on are these guys. Now that I got all of my y primes on one side, I'll just factor it out, leaving a 3y squared minus 6x behind, and it's equal to 6y minus 3x squared over on the right side. And so the final step to get y prime by itself is to just divide both sides by everything that isn't y prime. So that's 3y squared minus 6x. And I've got a y prime term. So back in the day, that's how we would solve for the derivative of y with respect to x if y is implicitly defined as a function of x. And I want to be able to do the same thing using the multivariable chain rule, because when we're looking in our three-dimensional space with x and y and z, we often look at z being our up and down variable as implicitly defined as a function of x and y. So I want to basically redo this whole process, but to solve for a z prime term instead of a y prime term. Most of the time, I'm going to be considering z as a function of x and of y. So we're going to get this fancy form where I'm going to pretend that I've got my function of x and y is equal to a constant. To make this an analogy back to what we would have done in like algebra and then next in Calc 1, I can really take any function that I had from algebra and write it in this form, f of x and y is equal to c. So take any function you can think of, it'll be of the form y equals something, like maybe y equals ax squared plus bx plus c, or even more simply, y equals mx plus b. And if I want to put it in this form, where I've got a function of x and y is equal to a constant, just subtract the y over to the other side. And then you've got that. Right? So if I had y equals mx plus b, that'd be the same thing as 0 equals mx plus b minus y. Let's kind of move that over. And then that's the form that I want to have. But it is important in the way that I'm defining these things implicitly that I have a function on one side and a constant on the other. Most of the time, that constant's just going to be 0, because if I just subtract c over to the left, then I'm left with a 0, and I can just absorb c into that other function. So most of the time, we'll just be setting these things equal to 0, so it just ends up in the form that we want, because then we have a very nice formula for finding these implicit derivatives, where it's just negative the x partial over the y partial. I'm looking for dy over dx. But one thing I want to point out is that the variables swapped position in the fraction, right? So now I've got my x partial on top with my y partial on bottom. But hopefully, well, I'll come back to an idea later on. For now, a quick sketch of where this thing comes from. If I just do a partial derivatives of f with respect to x and with y, I get the collection that's over there. I'm going to move the x partial over to the other side since the derivative of any constant is 0. Also notice the x over dx, or the derivative of x with respect to itself, is just 1, which is why you don't see that term here in the third line, right there. This dx over dx disappeared. It's just not there anymore because, again, set it equal to 1. And then I could divide my f partial y over and end up with dy over dx, the negative f partial x divided by f partial y. There's a lot other fancy stuff going on that we won't get into since we aren't really a proof-based class. We look more just at getting through some of the calculus part. But there's this implicit function theorem that you might see in a later math class, but we won't really talk about here. But let's do that same problem again, but with this new method. So finding dy over dx, or y prime, but we'll go at it this other way. So the first thing I want to do is define my function, function of x and y. It should be x cubed plus y cubed minus 6xy equals 0. Because again, it's important for this function to work, or for this formula to work, that my function is equal to a constant. And again, most of the time that constant will just be 0. Slide you over to the left a little bit. So now I need x partials and y partials. F partial x is going to be 3x squared minus 6y. And my y partial should be 3y squared minus 6x. So then to come over here and get dy over dx, that is negative f partial x over f partial y. Again, my x and y are going to switch places here so that the x partial is now on top. It's in the numerator of that fraction on the right side, and the y partial is in the denominator. But if I just bring all that stuff in, this is what? 3x squared minus 6y divided by 3y squared minus 6x. 3y squared minus 6x. And then if I just distribute my negative through the numerator, I'll get exactly what I saw in the example I did first. Negative 3x squared plus 6y divided by 3y squared minus 6x. So a nice thing about setting it up in this form is that often we might find that these implicit derivatives go just a little bit faster than trying to go all the way through the chain rule of every problem. So again, we'll just use some implicit derivatives to kind of speed up our work a little bit. Our goal was to upgrade our original implicit derivatives from Calc 1 to a Calc 3 idea. So that we'll mostly be looking at the derivatives of z with respect to x and y, because we'll be defining z, at least implicitly, as a function of the other two variables. That's our hope and our dream. So z can be that implicit function. So again, we'll just gather up all of our terms on one side, have it equal to 0 on the right. Again, the constant won't really matter because we're taking derivatives of both sides, meaning derivative of constant is always 0, so it doesn't matter which side that constant ends up on, because its derivative won't matter. So let's go find our function here. So f of x, y, and z, I'll just call it f for simplicity's sake. It is yz plus x natural log y minus z squared. Really some fine ambiance in this room today. We equals 0. Okay. Again, it is pretty critical that I get equals 0 over on the other side. So before I start, I just need to make sure all of my terms are on one side. And then I can start taking a bunch of derivatives. I'll look at f partial x. I'll just go right down the line alphabetically. That looks like the natural log of y. Sorry if my natural logs look like h's. It's supposed to be a cursive ln, but my handwriting's kind of bad. At least right there it is. Cool. So x partial, I only get the one bit. It's the natural log of y. I also need a y partial, which looks like it's going to be z plus x over y. The derivative natural log of y would be 1 over y. Hold the x constant. It's just a y partial. That's what I get. And then I want a z partial for my last term. It looks like it's y minus 2z. And then I want to go find a couple of things. The derivative of z with respect to x and the derivative of z with respect to y. Maybe for shorthand, I'll call that z partial x. But it is negative. The x part goes on top, the z part goes on bottom. So my x part was natural log of y, and my z part was y minus 2z. And I'll leave it right there. The other one that I wanted was the derivative of z with respect to y. I'll write this one out in its full notation just to, I don't know, emphasize that they can be written either way. We'll know what you mean. This guy should be a y derivative on top and a z derivative on bottom. Don't forget the negative sign out in front. But my y partial was z plus x over y, z plus x over y, and my z partial is still y minus 2z. Okay, and this is our last example, which is mighty kind. So again, let's go look for another derivative using this implicit stuff. Don't forget to redefine your function so that everything is on one side. E to the y sine x minus xy equals 0. I'm just going to keep highlighting that all the way through. Make sure that we're seeing that each time we do this thing. And find some more partial derivatives. I would like to get f partial x. And it is e to the y cosine x minus 1 minus y. And another derivative, but this time with respect to y, which is just e to the y sine x minus x. Well, minus 0 minus x, but I left the minus 0 part off. So in the end, dy over dx, that part's in yellow, that part's in purple, is equal to negative. Big old line. The purple part is on top and the yellow part is on bottom. This is e to the y cosine of x minus 1 minus y, and my denominator e to the y sine x minus x. And that's my implicit derivative. That one really went back to just a Calc 1 problem. So one final thing that I want to say about these implicit derivatives, and tying it back into something that I mentioned on Wednesday when we were looking at tangent planes. At least I think it was Wednesday. When we took derivatives of our three-dimensional functions and we went to go calculate what we thought was a slope, right? We had like an A and a B term that looked like they ought to be slopes, because if we're looking at the equation of a plane, A, B, and C, the coefficients attached to X, Y, and Z can kind of be thought about as how far you would move in each direction if you took one step. But we found when we set that all up, we had that A and B were equal to negative change in X and Y over change in Z, which was backwards from what we expected out of a slope, right? For a slope of one of these functions, we would probably expect to see change in Z over change in X, since Z is our new function variable. When we think about slopes, we expect to see our Z change on top and our X change on bottom, but we get the opposite reciprocal of that. We get our X change on top, our Z change on bottom, and a negative sign out in front, or same thing, but replace X with Y if you look at the Y side. Which still kind of makes sense because that looks an awful lot like the equation for finding a perpendicular slope. A slope that's perpendicular to the line that we have is the opposite reciprocal. Change the sign, flip the fraction, gets you a perpendicular slope. And I want to keep bringing that up because oftentimes when we look at derivatives of these shapes or these surfaces that are in 3 space, the derivative element that we want to look at is the perpendicular part. We want to look at those normal vectors instead of at the tangent vectors. And we kind of switch it up depending on which method makes more sense. But quite often looking at, again, the three-dimensional structures, the normal vector makes more sense to look at than the tangent vector. They're both very closely related because, again, we know what perpendicular slopes looks like. And when we did these implicit derivatives, the same idea comes up again. We still see that negative slope idea showing up right here. And we're going to look at that in a big way on Wednesday when we have the gradient. But anyway, that's enough for me. I'll stop class here. I will see you again on Wednesday. Okay, bye, 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 bye. Bye, 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 bye.